Class imbalance is a huge issue when training machine learning models. If you don't pay attention to it, you may think you have an amazing working model that achieves 99% accuracy, but in reality, it's not really that good. So today's video, we'll be taking a look at how you can identify class imbalance and then different ways that you could solve it, whether you want to oversample or undersample. Tons to cover, a lot of code to write, so let's jump into a little bit more of the background. All right, let's take a look at class imbalance. So class imbalance occurs when classes in a dataset are not represented equally. One class, which is the majority class, dominates while another, which is the minority, has fewer examples. Let's just take a basic example of fraud detection, right? It's a binary classification problem, which means you either have fraud or you have no fraud, right? And let's just assume a very basic level. If 99% of the data belongs to the majority class, not fraud, and then only 1% of the data belongs to the minority class, right? Which is fraud. So how you would be able to detect an imbalanced data set, the easiest way is going to be through EDA, exploratory data analysis, bar plots, pie charts, value counts. For example, over here, right, we have legitimate transactions versus fraudulent transactions. You can see 99% are legit, 1% are fraudulent, right? And if you're going to be training a model based off of this type of data, right, you have an imbalanced data set. And what happens when you have an imbalanced data set, right? So algorithms tend to focus on the majority class, leading to poor performance on the minority class, right? Imbalanced data may result in overfitting of the majority class or underfitting of the minority class. So accuracy could report 99% in a fraud detection problem by predicting all cases as not fraud, ignoring the minority class performance, right? And this is an issue because it leaves most fraud undetected. And when you're looking at fraud, you want to have it be the opposite, right? It's better to have a real transaction labeled as fraud than it is to not detect fraud in that case, because you always can ignore that type of transaction. Hopefully that makes sense. But regardless, right, imbalanced data set, we're not able to see the true correlations between the class and the features. And the goal is to create a balanced training data set, right? Usually you want to have a 50-50 ratio in binary problems for better model performance. So there's a few different ways that we can fix class imbalance. The first method is going to be called oversampling. And this is the most often used approach, right? It involves increasing the number of instances of the minority class to match or get close to the size of the majority class. Now, this could cause overfitting on the minority classes, or at the same time, the model might be able to memorize what is going on. Or another instance, right? Since you're creating synthetic data, right, it increases the redundancy, which might result in models just memorizing rather than generalizing. Now another method is going to be called undersampling, which involves reducing the number of instances of the majority class to match or approach the size of the minority class, right? And this has a trade-off too. It risks losing valuable information in the majority class, but what this does is it removes or merges samples from the majority class to balance the data set, right? Undersampling works better for data sets with high redundancy in the majority class, but is less effective when the majority data is sparse. Another way you can fix this is cost-sensitive learning, right? So many algorithms, you can say like a logistic regression, decision tree, random forest, support class weight adjustments to balance class representation. So when do you want to fix class imbalance? You want to do this after your train test split, and you only want to do this with our training data, right? If oversampling before the train test split, there's a risk of data leakage where identical samples appear in both sets, right? And to prevent this, apply resampling techniques exclusive in the training data set. And in our code today, we're going to go through all these examples, right? We're going to go through undersampling, we're going to go through oversampling, and we're also going to go through cost-sensitive learning. Lastly, what metrics should you use on class imbalance, right? As I showed you earlier, accuracy score never helps when you have an imbalanced data set. So typically when you use like a precision recall or F1 score or a confusion matrix. So with this out of the way, let's grab a Python notebook and start coding. All right, so before I do start coding, few things. Number one, where I'm going to grab the data for this video, there's this credit card fraud detection data set here on Kaggle. So just download this over here. And then what we'll do is we'll drag this in. And I've already done this. So just click this folder icon and drag in creditcard.csv. Again, I'm using Google Colab. Feel free to use whatever you want. But this is the data that we'll be using for the video. And again, also, my intention on this video is not to make this a project on the credit card fraud data set, right? We're going to use very entry-level machine learning based around this, but just to show you a few different ways that we could address class imbalance. So with that out of the way, if you do want to see a full data science project around this data set, just let me know. I'm kind of like 50-50 if we should do it or not on the channel. Obviously, it will take a while to build out that type of video between the production as well as testing out the code and everything like that. But I think it's needed for the channel. So again, just let me know. Okay, so what we're going to do first is we're going to bring in a bunch of imports. So always kind of tedious at the beginning, but regardless, we're going to do import pandas as PD. Then we're going to import numpy as np. Then import matplotlib.pyplot as plt. Import seaborn as SNS. From sklearn.model selection. Imports train test splits. We're going to go super basic with our model, and I misspelled from above over here. We're going to say from sklearn linear model. And yes, I know there's going to be other models that perform better. Again, keeping it basic for this video, we're going to just use it import in a classic logistic regression. Oh boy, super easy. All right, then we're going to bring in some metrics. So sklearn.metrics imports confusion matrix, F1 score, accuracy score, from imblearn oversampling imports SMOTE random oversampler as well as ADASYN. I think that's how you pronounce it. If not, just let me know. Now we're going to do the same thing for undersampling. So I'm literally just going to copy this. Undersampling imports. We'll use the random undersampler. And we'll just do one more. Edited nearest neighbors. And then from sklearn.preprocessing import our standard scaler. All right, I think that should be everything. Of course, I misspelled logistic regression, and it failed because I misspelled logistic regression. That's all right. Good start to the video, right? And yeah, let's get going. So what we're going to start off with is loading in our data set. So we'll say df equals pd.readCSV, and then what we're going to do is grab our CSV. And how we're going to do this is just click these three dots over here, click copy path, paste path in here, and we don't have to type it out, and it gets our path for us. So this will take a second to read our CSV. Then just to make sure that this is working correctly, I always just do a head or a tail. Head, look, boom, good. And we're ready to go. And all right, we're going to start off with some simple EDA. So we'll say simple EDA. And what we're going to start off with is looking at the value counts. So we'll say df, we'll have class over here, and just do .value counts, like that. And this will tell us how many fraud versus non-fraud. So majority of the transactions, right? 284,000 not fraud, 492 fraudulent transactions. And again, we're going to keep this basic. Let's just do a quick figure. So we'll say plot figure, say fig size equals 64. Then sns.countPlot, x equals class, data equals df, plt.title, class distribution. We can show this plt.show. All right, and just make sure C is capital. And you'll see over here, right, exactly what I showed you here, but this is just plotted out, which shows you, these classes are completely imbalanced. I mean, there's a lot more non-fraudulent transactions than fraud, which is a good thing, right? You don't want to have it 50-50. As a business, having 50% fraud versus 50% non-fraud. So good real-world example, but when we train our models, we don't want to have this. So All right, so now what we should do is set up our data for the video. And we'll split X and Y. So we'll have capital X and then we'll have Y. Y is literally just going to be equal to df class. So class like that, basic, right? That's what we're trying to predict. X equals, and we're going to keep all of our features, right? But we're going to drop our class and time because we're predicting our class and time's not valuable in this instance. So class and time, and we'll say axis equals 1, axis equals 1, right? Because we want all those columns gone, and boom, gone. Great. And now what we can do is train test split. So x train, x test, y train, y test equals train test split, capital X, lowercase y, test size equals 0.2. We'll set a random state equals 42. Stratify y. Okay, and then what we'll do next is just a baseline model. So we are not going to address class imbalance, so we'll say baseline. Spelling is amazing today, but we'll say baseline model. Okay, and then we'll set our model. And again, it's a basic logistic regression, right? So logistic regression. Inside over here, we'll say max iter equals 1000. We'll have random state equals 42. Awesome. Now let's have our model fit our data. So we'll say model.fit x train, y train. All right, and this is running right now. While this is running, I'm going to make predictions. I'm not going to run that code yet, but we'll say y predictions equals model.predict. We'll have our x test in over here. Awesome. And then just to show you, right, if we take a look at our accuracy score, we'll pass in y test, and why this isn't the best metric, right? Y prediction. And you'll see that we achieved 99.9% accuracy. Wow, look at that. Our model is awesome. And then if we take a look at our F1 score, right? And we'll pass in our y test and y prediction. We get 72. It's already showing you the accuracy score is already a bit too high. And then lastly, let's take a look at a confusion matrix. So we'll say CM equals confusion matrix. Pass in our y test, pass in our y prediction. Then we'll do a plt.figure. Fig size equals 64. sns.heatmap, sncm, annotate equals true, formats equals decimal, format D, cmap blues, x tick labels. I just zoom up a little bit. Scroll up, not zoom up. Exit labels equals, we'll have non-fraud, also fraud. And we have our y-tick labels, which will be the same thing. So just copy that. Right. Now we need to do our x and y. So x label predicted labels, y will be actual. I meant to do a new line, apologize there. So labels. Then we'll have plt.title, confusion matrix, plt.show. All right. Okay, and now analyzing this over here, right? So first thing is on the fraud side of things, we had 63 that we predicted were fraud and were actually fraud. Then on the non-fraud side of things, right, there's 35 that were fraud that we classified as non-fraud. And then over here, right, again, we had fraud and 13 that we said were fraud were non-fraud. Now, in perspective, right, and from working in the fintech space, it's better to have more over here, which we think are fraud, that aren't fraud, than down below over here. And the reasoning is we could have like an analyst or something like that take a look at the case closer and say, hey, this isn't fraud, don't worry about it. Like we want to have this number as low as possible, right? Obviously we want to have as much fraud predicted correct, but between both of these, this is the more important metric, right? Because if you miss fraud, that could lead into large losses. So this is our first case, right? And we'll go through oversampling, undersampling, and change some of the weights and see if we could improve this. And yeah, let's start off on that side of things with some oversampling techniques. Now, these aren't guaranteed to work to make our model better, and there's a lot of other ways that we could improve the performance, but we'll just take a look at just from our sampling, right? So we'll start with oversampling. So oversampling, and we'll start off with the random oversampler. So we'll say random oversampler equals, or ROS equals random oversampler. And to set a random state, so random state equals, we'll say 42 like everything else, right? And then what we'll have over here is we have to resample our X and Y. So we'll say X equals X resampled. Then Y resampled equals ROS dot fit resample. Passing our X train and Y train. So X train and Y train. Great. Then what we're going to do is show you the plot now that these are over here. And the first thing we'll have to do is set up class counts. So we'll say class counts equals Y resampled value counts. Right. And actually, I forgot it. The this Y resampled. So now this should work. We could print this out, or we could just plot, and just to show you what this looks like, right? You have our two classes, and they're equal values now, right? Which is great. 227451. But let's also just plot this out. plt.figure. And we're going to reuse a lot of this code throughout the video. So just as a little bit of a heads up over here, we'll have the fig size, say plt.bar of our class counts.index, class counts.values, color equals, well, blue and orange, no matter. We got x ticks 0, 1. Class 0. Could label this also instead of class 0, class 1, fraud, non-fraud. Okay, plt.xlabel class plt.ylabel count plt.title class distribution after resampling, and then just show this plt.show. Right. And class counts, it should be class counts. Twice class counts. And here you go. So you can see that these are equal now. And, you know, this goes the opposite of what we had earlier, right? Where non-fraud dominated over fraud, these are now equal, right? Both over here, they both had this 227451 in their class. And let's see what happens with our model. So now what we want to do with our model is we want to fit it based off of this resampled data. So we'll say model.fit, and we'll have X resampled, and then Y resampled, like that. And I'm going to let this run. It's going to probably take a minute or so. And then we'll do our prediction. So Y prediction ROS equals model.predict our X test. So you still want to predict on your X test over here. And then we'll take a look at two things, right? We'll look at first our accuracy score on this side of things, right? And I still don't want to use our accuracy score in general, but we'll do that. Y test, Y prediction ROS. What I care more about is our confusion matrix and our F1 score. So we'll say F1 score, we'll pass in again, Y test, Y predict ROS. And then what I'll do too is set up our confusion matrix, which is going to be the same code essentially as what we had above. I don't want to copy all this code again, right? It's a lot. So, or write it all, I should say. So what we're going to do is just pass in this Y predict ROS. So I'm just going to pause the recording until this model is done fitting, and I'll be back once it's ready. Okay, so it finished fitting. Probably took about 2 to 4 minutes. So what we'll do is now get our Y predictions. We'll get our accuracy score. Our accuracy score did go down. You can see it went to 97.4, right? Look at our F1 score. Our F1 score is pretty atrocious, 0.11. And let's see what's going on with the confusion matrix. So what's interesting now is on our non-fraud side of things, right? There's only 8 predicted labels, and you can take a look over here. There's 35 in the past, right? So that has gone down, which is good, right? Let's see if our fraud versus fraud has gone up, which I assume it should, right? And it has. It went from 63 to 90. One thing to note though is this fraud, which ended up being non-fraud, skyrocketed, right? We see 1439 over here, but our first example, we only had 13. And that is a lot of resources used, right? 13 versus 1439. So, you know, if there was a super fast way to determine if fraud wasn't fraud, right, from an analyst perspective, someone on your team taking a look at it, maybe this would be the better model, right? And also if you care about, you know, detecting fraud the most, you know, this did a better job at detecting the fraud, but it also misclassified a lot of non-fraud as fraud, which we saw evident from this 1439. This led to a lot of overfitting, right? That's why we got a F1 score so low. And again, like our accuracy score is a 97, and like look how much over here that we classified as fraud and isn't non-fraud, right? Again, don't use your accuracy score as much. Doesn't tell you a lot of information. Our confusion matrix really does. So does our F1 score. So let's go over another oversampling method. We're actually going to go over 3 oversampling methods. And this next one is a little bit more popular. It's called SMOTE. Maybe it's SMOTE. But yeah, let's jump into it. So we'll say SMOTE equals SMOTE, like that. And we'll say random states equals 42. And there, again, what I'll also say is there's a ton of different oversampling or undersampling methods out there. Some of them will take a very long time to run. Some of them are a little bit faster. So I'm only showing you a few of them. Go online, research them, test them with your data set, see what will work best for your model. But yeah, this is just 3. On the oversampling side, I'll show you 2 undersampling, and I will look at some of the class weights. So here's SMOTE, right? And again, we're gonna have to resample. So X resampled, Y resampled, right? Resampled equals SMOTE.fit resample, and pass in your X train and Y train, right? X train, Y train. Great. And then what we'll do again is just look at our class counts. We don't need to plot everything. If you guys want to, you can. Just to show you this on this. We'll plot again when we go to undersampling because both won't have the same exact results with undersampling. But yeah, so we'll have our class counts and we'll just print this out, right? Or just literally say class count. It doesn't really matter, to be honest with you. And you can see again, 227451, okay? And what we'll do now is we'll fit our data. Again, this is gonna take a little bit longer. So we'll say model.fits and we'll pass in our X resampled and Y resampled, which you could technically just grab right here. I misspelled resampled, so I apologize on there. For some reason today, I cannot type. And that sometimes happens when you record a video. Technically my second video recording today, but it does happen. So this is fitting. While this is fitting as well, what I'll do is we'll set up our prediction. So we'll say y prediction SMOTE equals model dot predict on our X test. Right. Then what we'll have next is our accuracy score. So we'll say accuracy score. We'll pass in our Y test as well as our Y prediction SMOTE. And then we'll do F1 score. So just grab that, put F1 first. And then lastly, what we'll do is our confusion matrix. I just have the code next to me, so I'm just gonna copy this over. Just because it is a lot of work just to scroll back up over here. So we have our Y test, Y prediction. It's gonna be the same thing, right? So what I'll do, I'll pause the video. Once this is done running, I'll restart it and we'll keep going. But a lot of these models, after we do our resampling, are gonna take a few minutes. And kind of the reason why I just did a logistic regression. It's pretty fast also. So yeah, I'll be back. Okay, so literally as soon as I said I'll be back, this model finished, which is kind of sad on my side of things. I'm like, dang, I have to split this video up. But regardless, let's do our prediction, right? Let's grab our accuracy score. Our accuracy score is 0.98. So again, that is a little bit of an improvement on our accuracy score, but that metric does not matter to us, right? It's not the best to look at this. Our F1 score also improved slightly, but it's still pretty atrocious at 0.14. And if we take a look at this confusion matrix, right? A few things. Number one, there was one less or one more over here for non-fraud versus fraud, right? So if you go back up over here, right, we had 8. Now we have 9, and that compares to 89.90. So pretty close, but again, it depends on how you view this, right? A fraud miss could be $10,000, if not more sometimes, depending on the account, if there's liability or not. But what is nice, if you take a look at this fraud, which turned out to be non-fraud, we see 1065 versus 1439. So again, there's always trade-offs, but it looks like this one's performing a little bit better, right? About 400 less over here. Obviously, a little less performance on the fraud versus non-fraud, and it's only 1, which isn't a lot, versus 400 down over here. So if I had to choose, I'd probably go with this model over here. If you're looking at the class imbalance, right? If you had to use either random or SMOTE. And let's jump into another one. So now we're going to look at ADASYN, right? So we'll call this over here. We'll say ADASYN equals ADASYN, the random state equals 42. And one thing we're going to have to do if we use ADASYN is use a standard scalar. So we'll say scalar equals our standard scalar, like that. And then also what we're going to do is scale our X-train data. So we'll say X-train over here, scaled equals scalar dot fit transform. Pass in our X-train. And I misspelled fit transform, so I'll just do that again. Form like that. And Again today, I'm typing terrible. But here we go. And now let's look at a resampled. So we'll use X resampled, Y resampled equals ADASYN.fit resample X train scaled and Y train. Okay. And then what we'll take a look at is our class counts. So we could literally just go up here, grab this code again. And we'll look at class counts. And you can see 227468. Awesome. And now we will fit our model. So say model.fit, pass in what we have over here, X and Y resampled. And while that is running, we'll do. And actually that ran really, really fast. So we'll look at X test scaled now, and we'll say this is equal to scalar dot transform, pass in our X test. So we're gonna have our data scaled. Then we'll have over here is Y test ADASYN, or then we'll have over here is Y prediction ADASYN equals model dot predict, and pass in our X test scaled. Right. And then what we need to do now is take a look at our metrics again. So I'll just copy these over here. Right. Accuracy and F1. So let's see how these did. So we'll pass in our Y predictions, right? Still have the Y test. So accuracy score went down significantly, right? We have 0.913. Our F1 score also is doing really bad, 0.03. Oof, that's not good at all. Already telling me we're going to overfit. And what I'm going to do is paste over this confusion matrix code. I will pass in our Y prediction over here. And look at that. So again, we did a little bit better job of our predicted labels over here with the non-fraud versus fraud. Right now down to 7, but it's not reasonable, right? You have 4915 that are now classified as fraud that are not fraud. So didn't really perform that well based off of this. I mean, again, if you only cared about this down below, maybe, but 4915 is still pretty bad. Those are our first 3 for oversampling. Now what I want to do is show you 2 for undersampling. So we'll say undersampling, and we're going to start off with random undersampler. So random undersampler. All right. And we'll say undersample equals random undersampler, random state equals 42, Jackie Robinson. So we have undersampler over here. We'll say X resampled under, Y resampled under equals undersample dot fit resample, pass in X train, pass in Y train, like that. Great. And we can do our class counts again. So grab that code. And I'll stop scrolling up after this one. So I do have the code right next to me to the side, so I guess I probably should use that. Anyways, so we'll grab this over here. Y resampled under value counts. We'll look at our class counts, right? And you can see now we're at 394. So way smaller data set now on this side of things, right? And if we have it even, once again, kind of like random oversampler. Well, the random oversampler, again, much larger values. Random undersampler, we're down to 394. So a lot less data to train on, right? So what we'll say is model.fit. For here, we'll have X resampled under, and we can just grab both of those right here. Right. Awesome. So we have both of these over here. We can do our Y prediction. So Y prediction under equals model dot predict, pass in our X test, right? Then what we'll do next is look at our metrics. So we can look at our accuracy score, which is 95.9. Then we can take a look at our F1 score. F1 score is pretty atrocious again, 0.07. And let's just visualize this. And on the visualization side of things, right? 22, 99, 90, and 8. So not the best. We had one, I think that was 98 and 1,000 a little bit earlier. So probably not the best approach to use. Again, we're not doing a full project based around this. There's other things to explore. But regardless, that's our first for undersampling. And what I want to do is another one, which is edited nearest neighbors. And what I will also mention is some of these for undersampling will take a very long time to run. I believe this was one of them that took a while on my computer. So we'll go through it, pause it, we'll go forward again. But that's also why I'm only showing you two in this section. And yeah, there's lots of them out there. I think I've already said that like 3 or 4 times, but keep on testing, right? So we'll say edited nearest neighbors equals edited nearest neighbors. That's not really too special there. Then we'll have, it's the same as a little bit above, right? So just grab your X resampled and we'll just change that for edited nearest neighbors. Still have our X train and Y train. So that fit resample. And then what I'll do next too is take a look at our class counts. But this is going to take a bit. So I am going to pause the video right here. And we will be right back once it's ready to go. All right, so this is done now. And I just did the class counts. And we get a value of 227304. Now, a few things. Number one, when we used our random undersampler a little bit earlier, right? You'll see that we had the 394 count, right? And those were the same for both. When we looked at edited nearest neighbors, we had 227304. Now, this number looks pretty close to what we had above, right? And I'll just go all the way up to show you. It's not the same. We had 227451. And now we're down to 304. So we're down 150 samples in our 0 class, which was not fraud. And it's just based off of how our edited nearest neighbors work, right? Not all undersampling techniques is going to have both classes be 1-to-1, right? And to get the exact verbiage of the edited nearest neighbors, right? It says this method cleans the data set by removing samples close to the decision boundary, removes observations from the majority class or classes when any or most of its closest neighbors are from a different class. So I cleaned up our data a little bit, right? It took a while, but just wanted to call that out because you may look at these class counts and be a bit confused why it wasn't 1-to-1. It's not always going to happen in that instance, right? So now what we want to do is fit our model again. So we'll say model.fit and we'll pass in our X and Y resampled under. So we'll grab both of these over here. This may take a minute or two because we do have quite a few samples. And we'll do our Y prediction. So Y prediction under model predict our X test. Then we'll grab our accuracy score, right? Y prediction under, we'll grab our F1 score. And then we can visualize our confusion matrix, right? So we have all of those over here. Again, I'll pause the video. Once this is ready, we'll restart it and we'll take a look. Obviously, this is still imbalanced quite a bit. So these results are going to be probably pretty close to the first model that we ran in the video. Actually, this ran not too bad. It's already over. So let's just run these, right? So accuracy score, again, 99.9. I'm predicting that this is going to be pretty close to what we had earlier. F1 score 77, right? Which is actually an improvement. We had 72 earlier. And let's look at this. So take a look at that. 70, 28, and 13. And I'm just curious what our first one was, right? And we'll scroll up and check it out. So we got a little bit of an improvement, right? This 13 number was still there on both of them, but we had 70 in the fraud versus 28 for non-fraud. And that was just by implementing in edited nearest neighbor, right? So this is definitely an improvement. It's not perfect by any means, right? You saw earlier, like some of our other cases of oversampling had closer to 90, right? So if we just go back over here, where was that at? Like we had 91 there. But our side of things where we predicted fraud and it was non-fraud is down to 13 and a subtle improvement. So again, you can keep testing different undersampling methods. They do take a while to run, but already a little bit better than what our baseline model was. So what I want to look at now is cost sensitive learning. So we'll do that now. And this is where we tweak the weights of our model. So we'll say cost sensitive learning, right? And we'll say model equals our logistic regression. We'll do our max iter, be the same. We had 1,000, right? Then we'll set a random state equals 42, and class weight equals balanced, right? So we have all that over here, and you make sure random state is not double capitalized right over there. And right, we set our weights to balanced, so we'll test it with this. We'll say model.fits x train and y train, right? We're not resampling anymore. And we'll see how this performs. So we have x train, y train. Let's do our y predictions, right? Y prediction model.predict. We have our accuracy score, our F1 score, and then we'll have our confusion matrix. So we'll take a second to run, and then once this is ready, we'll resume. Okay, so now let's do our Y prediction, our accuracy score. So our accuracy score is 97.4. Our F1 score is 11. And let's look at the confusion matrix, right? So we see 98. And then we take a look at our confusion matrix, right? 98 and 1447. So not that great, right? And just to double check, Y test, Y prediction, Y test, Y prediction, Y prediction. Yeah, so step backwards once we did the balanced on this side of things, right? We predicted more fraud, which is good, but our non-fraud side of things, where we thought it was fraud, was quite high. It was going back into what we took a look at for random oversampling. So unfortunately, that approach did not work well. And now what I want to look at is an example where we can set custom class weights. So a lot of this is going to be the same again, right? And what we'll do on this side of things is over here and set our class weights. So we'll say class weights equals, and what I'm going to say is for non-fraud, our class weight is a 1. And then if it is fraud, our class weight is going to be a 10, right? And I should say equals, not a minus sign. A little bit of a typo there. And then we'll say is our model, well, I already copied the code, but model equals logistic regression. We'll keep the max iter. We'll keep our random state. And then our class weight, we're going to say this is equal to class weights over here, right? And again, you can keep testing different class weights and see what works best. I just did 1 and 10 for the video. And we'll fit our data again. So we'll go over here, model.fit. And what I'll also do is we'll get the rest of the code ready. So we'll do Y prediction, Then we'll also go over here and do our accuracy score. We'll do our F1 score. And I'm curious, well, I already know the answer, but I'm curious whether our balanced or our custom is going to perform better. We'll also have our confusion matrix over here. And once all this loads, we can close out the video. So be right back once this is done fitting our data. All right, and you can see over here, class weights, we set those up. So it's at our Y prediction, our accuracy score. So accuracy score back up to a 99%, means nothing. Our F1 score actually improved again, 7.5. And let's take a look. So, well, now what we have over here is 83 fraud versus 15 non-fraud, and then 39, which I'm thinking this was our best, right? I'm curious what our edited nearest neighbor was again. And I'm just going to look at the code to my side screen and load that up over here. Where is this at? Logistic. Okay, so our edited nearest neighbors, I have this up over here, had 70 on this side of things. Had 28 and 13, but this has 83, which is quite a lot more, 15 and then 39. I actually like this one a lot, right? When we saw quite a few that were labeled as fraud but non-fraud, we had over 1,000 here, and this was with 90. So we did see quite a bit of improvement by just changing up the class weights in our model. So again, a lot of different approaches, right? I showed you class weights right now. I also showed you random, or not random, but just in general oversampling as well as undersampling. And again, there's a lot more that we could tweak, but that's about it for class imbalance. Let me know if you do want to see a full data science project on this. I think it would be actually quite fun, especially since I work at a fintech, and we could dive into a lot of things. So regardless, I hope you guys enjoyed it. So that is class imbalance. I hope you guys learned something new from this video, and if you did, make sure to subscribe to the channel. Also, if you do want to see a project based around class imbalance, I might be able to download another Kaggle dataset and we can walk through it. So if there's enough interest, just let me know down below in the comment section or in the Discord, and yeah, we'll make a video. Anyways, if you want to keep watching other machine learning videos, I have a playlist which I'll link down below, also right over here. So enjoy those videos.